Okay, so as I mentioned, this is just carries on from page 67 in the notes. Okay, so we've looked at 3 rasterization algorithms so far. DSC algorithm, absolute rubbish. No one ever uses it, too slow. The DDA is an improvement on that because you only have to add a number to calculate the coordinates. But we have a better one still than that. We have Breshenem's algorithm, which we looked at on Friday. Now, the reason why Breshenem's algorithm is so good is it only ever uses integers, only ever uses whole number arithmetic. Okay, so ideally, with circles, we'd also like to have a method which only ever uses whole numbers, and thankfully we do. So that's what we're going to be looking at this morning. It follows the sort of same concept as Breshenem's algorithm, as we'll see. Okay, before we start, we're going to have a look at a circle. Okay, there's a circle. This particular circle is centered at the origin. So you can see I've got Cartesian space. This circle is centered at the origin. Now, what I've done here is I've drawn a line, which is where y equals x. And I've shaded this point in here as a black point. Okay, the reason I've done that is if we use x as the driving axis, so remember, the driving axis is the one we add 1 to calculate the coordinate. Okay, so if we start at the 12 o'clock position and then use x as a driving axis, so add 1 to x each time, we're going to fill in, or hopefully, we're going to try and calculate all the points in this first octant. Okay, the octant going from about 12 o'clock to about 1:30 on the clock face. So this is the coordinate I'm trying to calculate, this dark one. Well, what we can do is with circles, we can make use of symmetry. Okay, obviously circles have got infinite number of lines of symmetries in them. Well, we can use 8-way symmetry. Okay, so let's say we have this one calculated here. Well, if I use alignment symmetry about the y-axis, I automatically know what the coordinates of this point is, because I simply negate the x-coordinate. So once I've got x, y, I also know what this point is. Likewise, if I use x as the symmetry, I know this point down here. So I simply negate y. Okay, so, and if I negate them both, I know this point. Okay, so if I've already got the coordinates of x, y, I automatically know the coordinates of this point here, this point down here, and also this point. Well, another thing I could do is if I use the line in symmetry about y equals x, if I swap x and y around, I also know what this point is. And again, negating y and x gives me this point, and this point. So in short, what this means is I only need to calculate points in this first octant. Once I've got those points, I can fill in all the other 7 octants. So we've immediately cut our work down to 1/8. Okay, instead of doing the whole circle, we only ever calculate 1/8 of the circle and use symmetry to calculate the other 7 points. Okay, so that's what I mean by circle symmetry. So you'll start to realize, or if you haven't already done so, in graphics, it's all about being as efficient as possible. You're doing the least amount of work as we possibly can. If you wanted to code that circle symmetry up in MATLAB, okay, I'm not going to show you the MATLAB code for the midpoint algorithm, which is coming in a minute. The reason being is it's part of your assignment. Okay, but I will show you this code. And what this code does is, given a raster, x and y are the x and y coordinates of a circle, given or assuming that the circle center is at 0, 0. Okay. C is center coordinates of the circle. So I assume for circle symmetry, the center of the circle has to be at 0, 0. But if I don't want the center of the circle to be at 0, 0, I have to add the coordinates of the center to it. Okay, so that's what C is. Color is your RGB color vector. Okay, so here we've got 8 lines of code corresponding to the 8 pixels around the circle. Okay, so what you notice here is I've got the center x coordinate, which is C1, plus x, and the center y coordinate plus y, and all the others are just combinations of x and y, plus and minus. So what this will do is it will return a raster with 8 pixels filled in, and those 8 pixels being 8 around around the circle. Okay, so that if you want to do the first additional task from assignment 10, you're going to have to use that somehow. Okay, so this brings us on to what we call the midpoint algorithm. It's actually the same as Brescian's algorithm, but using circles instead of using lines. So what we have is a very, very simplified raster here. Like Brescian's algorithm, I'm assuming the pixel at xi, yi has been illuminated. So we're assuming we know, but this pixel here, okay, with the center at xi, yi, is on the circle. And so what we do is we move to the right, and we've got a choice between this pixel or the one below it. Okay, so instead of going east and northeast, we go east and southeast. Okay, so this idealized line here, so this is the circle, lies somewhere between these 2 pixel centers. So I'm going to have to choose between these 2. So is yi or yi minus 1? And to do that, exactly the same way as Brescian's, we look at the error between, well, actually, we use an error, but with the midpoint algorithm, we use the error between the midpoint between those 2 pixel centers and an idealized line. So epsilon there is just the distance between yi minus a half and our idealized line. Okay, if that's positive, we render the top pixel. If it's negative, we render the bottom pixel. Or maybe the other way around, can't quite remember. It's one of the 2. So that's what we've got to do. So like Brescian's algorithm, we use this error. Okay, the error tells us, or the sign of the error tells us whether we render the top pixel or the bottom pixel. Okay, to calculate the error, we use a Cartesian equation of a circle. So x squared, that x is your x coordinate, y is your y coordinate of a point on the circle. X squared plus y squared equals r squared. Now r is the radius. So x and y are points on the circle centered at 0, 0. So if you want your circle centered elsewhere, you just add something to your x and y coordinates. Okay, so that's the Cartesian equation of a circle. Well, by simple rearrangement, okay, if we have an exact point on the circle, x squared plus y squared minus r squared should equal 0. Okay, so using the equation of a circle, if I just simply rearrange that by subtracting r squared from both sides, I got 0 equals x squared plus y squared minus r squared. That's for a point on the circle. For a point somewhere off the circle, that's not going to be equal to 0. So that gives us our error. So quite simply, for an arbitrary point anywhere on 2D space, we have this error value. It's actually simpler than the straight line one. So it's x squared plus y squared equals minus r squared. Okay, what I've got on this slide is sort of condensed. So I'm going to use a visualizer in a minute just to sort of fill out a few gaps. What we do is we assume we start at the 12 o'clock pixel. So that means your x coordinate will be 0 because it's bang but straight up, and the y coordinate will be r. And somehow we get this expression, and I'll show you how that is on the visualizer. Okay, so our starting point is our function of the error. And that just derives from Cartesian equation of the circle. Recall that what we do is we add something to the error. So with Brescian's algorithm last week, we add something to the error, so we've got to derive the change in error. So what's the first change in error between the pixel at the 12 o'clock point and the next pixel along? Okay, so our first error, which I'm going to call epsilon 0, is the error at the next pixel along. So if I've moved one along in the x direction, okay, so if I've got a simple, so that's what we got. Okay, there's my midpoint. Okay, so the error is the distance. Oh, sorry, the distance. So that's xi plus 1, yi minus 1. Okay, so this error is this distance here. Okay, we've got some error here and we've changed it. Okay, so we need the difference between this pixel or this midpoint. So that's 1. If x is 0, x plus 1 is 1, and r minus a half. Remember, this y coordinate was r, because we're at the 12 o'clock position. So this line here must be r minus a half. And from that, we subtract r0, r. Okay, so that's how the first error changes. What's the error? What's the difference between the error at this midpoint compared to the error at the center of the first pixel? Okay, so what we do is I replace, well, I use this function here. So first we got 1 squared plus r minus a half squared. Okay, so that's y. So that's that y squared minus r squared. And from that we subtract, okay, x is 0, so that's going to be 0. Y is r, so that's going to be minus y squared. And minus r squared, so that's going to be plus r squared. Okay, so if we expand out, well, we can cancel out those 2r squares straight away. If we expand out this, we have 1 plus r squared minus a quarter r. Oh, sorry, minus r. Yes, minus r plus a quarter minus r squared. Okay, so all I've done there is expanded out that little bracket. Okay, cancel out the r squares. So we've got plus r squared, that cancels out. Minus r squared cancels out. And we just got 1 plus a quarter, which is 5 over 4, minus r. Okay, so that's our original error. So that's what you initialize the error to be. 5 over 4 minus r. For all other steps in the method, what we've got to do is we've got to calculate the change in error. So to do that, we say the change in error is equal to the error if xi has been illuminated. Okay, what's the change in error between the midpoint at the next pixel along? Oh, sorry, midpoint at 2 pixels along, minus the error at the midpoint at the next pixel along. Okay, so 2 pixels to the right, what's the midpoint? What's the error at the midpoint? Minus the error at the pixel, 1 pixel to the right. Notice we have, this is yi plus 1. Okay, just make that a bit clearer. Okay, we don't know what that value is. We know xi and we know yi because we've just illuminated them. We don't know what yi plus 1 is. So what I can do is I can derive an expression for the change in error, which will be a function of xi, yi, and yi plus 1. Okay, so to do that, okay, I'm going to use this function up here. So evaluate this function for this. So I've got x squared. Now my x is xi plus 2. We've got xi plus 2 squared plus y squared. And y, in this case, is yi minus a half, minus r squared. Well, the r squareds are actually going to cancel out in a minute. And from that, I subtract minus x plus 1 squared minus y minus a half all squared plus r squared. So you can see the r squares will cancel out. Okay, and then all we have to do is expand out the brackets, multiply it all out, collect like terms, simplify, cancel out, etc. Okay, so if we expand out the first bracket, we have xi squared plus 4xi plus 4 plus yi plus 1 squared minus yi plus 1 plus a quarter. And I'm going to ignore the r squared. Okay, so that's that bracket expanded and that bracket expanded. From that, I subtract this one, so that's going to be minus xi squared minus 2xi minus 1. Okay, because remember we're subtracting. And again for this one, yi squared. Well, we're going to have minus yi, but then it's going to be plus, so it's going to be plus yi. And then we're going to have minus a quarter, but again it's plus, so it's plus a quarter. Oops. Okay, so if we collect like terms and simplify, so those will cancel out. What else will cancel out? We've got okay, if we collect like terms and simplify, 4xi minus 2xi is 2xi plus 4 minus 1 is 3 plus yi plus 1 squared. Okay, so that can't simplify. Neither can yi plus 1 minus yi and squared. And have I got a minus yi as well? Have I made a mistake here? Well, it should be anyway. You can see it for yourself. Plus yi. Okay. Yeah, that's him. I think I've made some sort of sign error around there, but you can do that yourself. Okay, so this is our expression for our change in error. We don't know what we're going to choose for the next pixel. So therefore, we have to do one for either case. So for example, if we go yi plus 1 is just equal to yi, so that means we just go across. Change in error. So the change in error, if we went to the east pixel, is 2xi plus 3 plus yi squared minus yi minus yi squared plus yi. Okay, because all I did there is replace yi plus 1 with yi. Okay, as you can see, all the y's cancel out, and we just got 2x plus 3. Do the same, but this time if we went to the southeast pixel, okay, so we've gone down 1, so we subtract 1 from y. Okay, so change in error to the southeast pixel, it's 2xi plus 3 plus y minus 1 squared, so that's that bit there, minus yi minus 1, so that's that bit, minus yi squared plus yi. And if you do all the cancelling out, eventually you get to 2xi minus 2yi plus 5. Okay, so what we got? So we got our expression for our initial error. These are all derived using that error, all derived using this, which comes from the Cartesian equation of a circle. Okay, that's our expression for our initial error. And then we've got change in errors of 2x plus 3 and 2x minus 2y plus 5. These, these at the moment are integers, but our initial error isn't. Okay, so very simple. All we do is we keep track of what the error is. If it's positive, we illuminate one pixel. If it's a negative, we illuminate the other. Okay, so that was the derivation of your change in error terms. Okay, so if we go back quickly to the slides. So that's where this came from. Okay, and derive that change in error. Okay, and then you choose whether you go to the east or the southeast. And that gives you your change in errors went to the east or the southeast. The problem we have is if I go back a slide, 5/4 is not an integer. It's not a whole number. If you remember, we're not interested in the value of the error. We're only interested whether it's positive or negative. So what we can do is if I multiply this by 4, I'll get 5 minus 4r. That's a whole number because the radius has got to be a whole number because we're dealing with pixels. So if I multiply the original error by 4, I get 5 minus 4r. If I multiply the change in error, if I went to the east pixel by 4, I'll get 8x plus 12. And if I multiply this by 4, I get 8x minus 8y plus 20. So all calculations now integer-only calculations. So it's essentially Brescian's algorithm, but for circles. Okay, so here it is written in all its glory. This is the algorithm. You need a raster, which is your pixel array. You need coordinates of the center of a circle and a radius. So that's what you need to calculate or draw a circle. You start at the 12 o'clock pixel. So x takes on the value of 0, y takes on the value of the radius, and the epsilon is your error, takes on 5 minus 4r. Okay, that's what you set, initialize at the beginning. While x is less than or equal to y, so that means we're only going in the first octant. We're doing 1/8 of the circle. What you do is you render or you illuminate the pixels, 8 pixels, so center plus or minus x, center plus or minus y, and combinations of those. So there are 8 of them. That's where that other code came in. So you just call that code there. If the error is negative, okay, you update the error using, well, you used to add 8x plus 12 to it. If it's positive, you add 8x minus 8y plus 25 to it. Okay. If it is positive, you step down 1 in the y direction. And of course, you always increment x because that's our driving axes. Okay, so it's quite a simple method once you sort of get down to it. It's very, very elegant, very simple, very quick. Okay. Sorry? Probably because I've made a error. Yeah, I made a typo. Yes, that should be 20 there because multiplying. What are we doing? We're multiplying 5 by 4. Yeah, it should be 20. Sorry about that. Have I made the same error here? Oh no, it's right on this one. Don't know why. Sorry. Yeah, you notice it is just add 20 there. Okay, so done in a flow diagram if you prefer. Some people prefer them expressed in a flow diagram. And that's what you get. Okay, so what I've done there is I've typed in the midpoint algorithm and I've used it just to draw ever increasing circles. One thing you do notice is when your circles have got a small radius, they do start to look a bit sort of like a diamond, really. But that's unavoidable because we're approximating it using pixels. But as you get larger and larger, your circle should resemble more of a circle. So if you ever use those like paint packages or drawing packages, which are your circles, they use the midpoint to calculate it. Okay, so that's enough of me talking. I want you to have a go at